Hello, my name is Greg Kick, and I am the current maintainer of Caliper, and this is the first in what I hope to be a series of short videos about how to use Caliper. Over the course of, explaining the tool to many people in many different ways via text, email, documents, whatever it is, I've come to learn that the best way to really get a feel for the process is just looking over somebody's shoulder, so I'm inviting you to do that today. The first video is going to be a pretty basic explanation of how you get a simple caliper benchmark up and running using Maven, Eclipse, what I think is a pretty common development environment for most people. We won't be discussing how best to run these in production. For the time being, this is going to be, very much focused on the development lifecycle. The version of Caliper we're going to be using is not the current release, which is 1.0 beta 1, because I want to show off some of the features that are in the soon to be released 1.0 beta 2 that really do help development quite a bit, I feel. So the first thing we're going to have to do is obviously make sure that we have a local version of Caliper. And we're just going to build it, and hopefully that'll just be a simple Maven command. I do want to point out that the change we're currently at is this revision, C07 or C067, etc. This is the version we're using. Any of the features we discuss should still work in subsequent versions, obviously, as they are all very much planned for 1.0 beta 2. So we are going to pretend as though we checked out. I don't want to make you guys wait and watch the progress bars, but we are going to check out a new version of Caliper using this command. And this directory right here shows what you would otherwise get. Just, your Git repository that matches exactly what we would have checked out. And we're just going to go into the Caliper subdirectory because we don't care about the examples or anything like that at this moment in time. And we are just going to Maven clean install. Maven's going to go through the entire build process, do a variety of Caliper tests. Recently we had issues where some of the things didn't work so well on Windows, but I think we've resolved this, and in 1.0 beta 2 our Windows support should be pretty well rounded out. So while this builds, we are going to pop over to Eclipse and create the new project. For our example, I'm going to do a Maven project. We can create a simple project because most of the things that Maven does for us aren't particularly useful in this case. I am going to add it to a working set for Caliper, but you're free to do whatever you want. And we'll give it a group ID. Caliper tutorial, artifact ID. Caliper tutorial sounds good as well. Name. Caliper tutorial. We don't need a parent or a description or anything like that. And we have a new empty Caliper, or excuse me, a new empty Maven project. The first thing we are going to do is we are going to set up our dependencies. Open up the POM. I personally do not like the graphical interface, so I always edit the XML. For the dependencies, the first one we're obviously going to add is Caliper. So if we give it a group ID of Google Caliper, and an artifact ID of Caliper, and the version is, in this case, we are again doing a pre-release version, so 1.0 beta and then snapshot, so that we get the latest one that we've installed on our local machine, the one we're building now. Another dependency we're just going to toss in there is JUnit. We need something that we're going to benchmark in order for this to be an effective tutorial, and I thought that a simple example would be factorial. So factorial, for those that aren't familiar, is a mathematical function that Wikipedia does a fantastic job of explaining. And it basically says that if you take a non-negative integer, say 5, 5 factorial is 5 times 4 times 3 times 2 times 1. And as an added bonus, Wikipedia gives us a big table of, a handful of n and a handful of n factorial. So we even have test cases to make sure that our implementation is correct. So let's go ahead and do the simple implementation of factorial. Um, we are, for the sake of simplicity, we are going to use ints and longs. As you can see from this table, we really should be talking big integers, but for the sake of the tutorial, we're sticking to ints and longs. So let's make a function that takes an int, returns a long, and we'll call this the recursive solution. So number is our n, and the result will be n factorial. So let's make a quick function that takes a number, returns that number, and we're just going to check that it's valid. We're going to say that if our number that we pass in is less than 0, throw new illegal argument exception. Otherwise, return the number. And that's just for convenience sake. We'll see how that comes into play. So back to our recursive implementation. We have a couple cases. Our base case is, and we can implement this as a switch on the number itself. We can say that if we are in the case where it's 0, then we can go ahead and return 1 as it's defined. Otherwise, now we have to do the recursive call, and we're going to tell it to return, and we're going to return recursive of number minus 1 times number. And that makes sense, right? So if we pass in 5, we are going to return 5 times recursive of 4, which is 4 times recursive of 3, etc., etc., all the way down to the base case, which is recursive of 0, and that's going to return 1. And we'll test this in a minute. Our alternate implementation, and we'll just go ahead and grab this line. Our alternate implementation is going to be the iterative solution. And the iterative solution actually will end up sort of reading a little more like you might write it on paper if you were doing it by hand. So again, the first thing we're going to do is check for a valid number. And otherwise, we are going to, calculate a result. And we're going to start with 1 as the multiplication goes. We'll see how that comes up in a minute. And so some int I, and we're going to start with the number I is, greater than 0, I minus minus. So this loop is going to work from the number that we are requesting all the way down to 1, which is, I is greater than 0. And for each iteration, we're just going to say that result not 1, I. The result is just going to be multiplied by I each time. And obviously, we're going to return the result. So, as an example, we go back to 5. We're going to start with 5, and we're going to say 5 on this first iteration times the result is 1 is 5. Then we're going to say 4 times 5 is 20, etc., all the way down to the bottom of the loop. And hopefully, we should get the same result. The next thing to do is obviously to write our benchmark. So we make a new class, and we're going to call this factorial benchmark. And factorial benchmark, formerly under 1.0 beta 1, you had to extend a benchmark class. Caliper actually has much the same API heritage as JUnit does, in that it used to be subclasses and naming conventions. Now we're moving to annotations like many users have requested. So we need to write a benchmark method, and formerly we'd have to prefix all these methods with time, but we no longer, with time, but we no longer have to do that. Now we can just call them whatever we want. We're benchmarking the recursive implementation, so it makes sense to just call this method recursive. And so what I'm going to do here is set up the timing loop. Now the timing loop is a funny little thing. The operation that we are benchmarking is a small operation. It's a small bit of code. And unfortunately, system.nanotime seems like it should be able to, measure something. If we take the difference of two calls to system.nanotime, we should be able to get, nanosecond granularity. Unfortunately, that's not the case. The call to nanotime takes some amount of time, and two subsequent calls back to back, the shortest interval it can measure is actually usually longer than some of the things we might want to benchmark. So we pass in this reps parameter, and we make a for loop to do whatever operation we're benchmarking as many times as the rep parameter supplies. And Caliper's responsible for figuring out the appropriate number of reps for you to get good results. So we set up int I equals 0, I is less than reps, I plus plus. And now our benchmarking code is going to go in the body of this for loop. In this case, we're going to call factorial.recursive. And now we get to the interesting thing. What goes into this parameter? What are we benchmarking? Now we could say, benchmark recursive of 5, figure out how long that takes. But that's not very realistic. So we need to put something more interesting here. And the way Caliper handles this is we provide the ability to pass in parameters. And that's using the param annotation. In this case, I'm going to call it number, just like I did before. And what this does is it says, okay, we have a parameter, and on the command line, we can specify this as number equals, and then, give it some numbers, 1, 2, whatever it may be. But most of the time, we don't want to do that, so we give some defaults. And all the defaults are specified as strings. So in this case, I think we can stick with 5. And then we might want a couple that take a little longer, say 10, 20. That seems reasonable for a good sampling for the default run. And so now we can pass in number. Usually in Caliper benchmarks, it's not always clear whether or not this makes a difference, but reading from a field is typically more expensive than reading from a local variable. So anytime I'm accessing data from within the timing loop, I usually like to make a local copy, just making sure that the JVM is doing the most efficient thing possible. So we can say int number equals this dot number, and now the access in the timing loop is always reading from a local variable. That's just sort of a easy best practice. The other thing we have to be concerned about is that the JIT is very smart. As the Java VM executes, it will find dead code. It is possible that the JIT will recognize that we are never using the result of this computation and then, essentially comment it out. In order to prevent that, the trick we commonly use in benchmarks is to make a dummy value. This dummy value, call it 0 for now, and we return that dummy value. You might have noticed that I accidentally typed long before. I've sort of jumped the gun on that. In the timing loop, we do a very cheap operation that updates the dummy value, but with as little cost as possible. And I usually do or equals, so, dummy, or equals that result. So whatever comes out of recursive, we know that it's correct. We've unit tested to make it correct. We don't have to do any assertions. But now we just OR together all those numbers just to make sure that when we return the dummy, this call doesn't get eliminated as dead code. By the way, if you're doing something with objects, the cheap and easy way a lot of times to sort of apply this pattern to objects is to just, OR together the hash codes or whatever it may be, because typically hash code is cheap, but obviously, that might not be the case for your particular object. And in the event that it's not, system.identity hash code, I believe, is a good substitute for that as well. Anyway, so now we've set up this benchmark method, and we've got one for recursive, and we can just take this entire thing, make another version for iterative. We now have two almost identical methods. One benchmarks the recursive implementation, one benchmarks the iterative implementation. And we have ourselves a benchmark. So now we go back to the terminal. An excellent Caliper has gone through and successfully compiled, tested, installed. Everybody's happy. Now we need to go ahead and run our tutorial. So I happen to know that mine is located in my Eclipse workspace under Caliper tutorial. Excellent, that looks exactly like it should. And just to make sure we can Maven build that. Oh, build failure. Oh, sorry, Maven compile. And everything's looking good. So how do we execute this? We execute this now, and again, this will not work in 1.0 beta 1, but this is very much the preferred way to do it in 1.0 beta 2 and beyond, and certainly anything that you build from head. We are going to use the Maven exec plugin. So if we say exec Java, what this does is this, pulls in all of our dependencies for us, be it Caliper, be it anything that the code we need to benchmark relies on, etc. And we're going to tell it that our exec.main class is com.google caliper.runner Caliper main. This just invokes Caliper, and then the class that we want to benchmark, in this case we're going to copy the qualified name here, is our first argument. So the exec plugin takes exec.args equals is our fully qualified factorial benchmark. And if we hit this, we have to download a whole lot of plugins because I haven't run it on this machine. Excellent. And Caliper is off and running. Again, while this is running, I want to remind everyone that this is not going to provide suitable data for making a production decision. This is purely for development. This is running it. This is getting the right information, making sure everything looks moderately sane. The computer that I'm running right now obviously has the terminal, has Eclipse, has screen recording software, all this stuff, and is nowhere near the configuration of my production machine. I do not run production iMacs, as you might imagine. So the data that we get out will be, it will contain all of this information. It won't try and masquerade as a production machine. So you'll be able to tell back when you look at your data later whether or not, or what type of environment this was run on. But again, things like continuous build machines are really bad for running benchmarks, just because at the end of it, you're going to have data that's probably not reflective of what you might actually see in your running, be it servers or Android devices or whatever it may be. So keep that in mind. The other thing I want to mention is, as this thing is running, the data that gets printed. So what it tells us is it's going to, by default, and this always happens on, every default invocation of Caliper, is that it's measuring the amount allocated and the amount of runtime that it took to perform the operation. As we might imagine, there will be very little allocation because we didn't have any objects. This was, purely manipulating primitives on the stack. So the allocation should just verify that that's the case, and then runtime will give us the difference in runtime between the two results. It also has our parameters. Again, you have the defaults of 5, 10, and 20, but the we showed you how to specify those on the command line if you'd like. The virtual machine is interesting. We could have specified via the VM flag various virtual machines to run on, but again, this was just sort of a development exercise, so we used the default, which is whatever virtual machine you invoked Caliper with. Otherwise, Caliper would spawn a specific VM of your configuration. And then the selection type is always, at the moment, full Cartesian product. And what this means is that for every benchmark method, for every instrument, for every parameter or set of parameters for every virtual machine, it is going to, come up with every possible combination of those things. And that's what we're seeing here. We're seeing first we did the allocation instrument, the iterative method, the default VM, and 5. Then the only parameter it changed was the number. Now, once we work sort of our way down, we work our way down the list, then it went through allocation with the recursive benchmark method. Now it's onto the runtime instrument with the iterative, and then we'll see the runtime with the recursive. And that's how we get our 12 experiments, just multiplying each of those, each number of parameters together until we get this full set of all of the experiments that we might run. One last thing to mention about the difference between developing Caliper benchmarks and executing Caliper benchmarks for making production decisions is that we are obviously only running one trial of each. The Java virtual machine is somewhat non-deterministic in its performance. It's a profiling compiler, so the happenstance of the execution sort of matters a great deal in certain circumstances. So we at Google certainly do this for all of our production-related decisions. We recommend running with several trials. I mean, 3 at the very minimum, and hopefully many, many more of each of these experiments. Just keep running those trials so that we get not only information about a certain number of invocations of a method, but a certain number of invocations in a variety of JVMs, even though they're configured the exact same way. Seeing the differences from JVM to JVM can make a very big difference. So we are almost done with our execution, and as you notice, as this thing is executing it, it's telling us that it's complete, but it's certainly not mentioning any numbers. The specific reason for that is that there is a lot of data being gathered, and what we found is that oftentimes people will look at the information on the console, copy and paste it, and say, this is my proof of performance guarantees. And unfortunately, there's too much data to represent and too much subtlety to the data for the console output to really ever be valid. And we've been, talking about how to develop that, to, walk that fine line between giving people data that's useful for development, but, won't be misconstrued as, data for production decisions. But anyway, our benchmark has completed. It's collected 162 measurements, which again is somewhat difficult to put all on one console report. And those have been uploaded to this web page. And this is a strategy we've sort of settled on for dealing with micro benchmark data, is to always upload them to this web app. We can go ahead and take a look at that now. So these are our results. We have a table, and I claimed just recently that there was a lot of information being collected, but this looks like a relatively simple table. We've got, method name, this is the method that we ran, and we've got how many parameters. This isn't the most useful view for comparing things. We're trying to compare the iterative versus the recursive, so let's go ahead and move this column to the left. And there we go. So now we've got, 410 iterative and recursive for 20 iterative and recursive. And we've got some data over here, and you can kind of see, but it kind of looks like these bars are a little hard to distinguish. So we can choose this column and say use it for colors. And now it becomes clear. We've got our orange for the recursive, we've got our blue for the iterative, and it looks like our iterative solution is far and away the winner. In this case, I would say that we're not allocating extra stack frames, we're not doing all that work. It's just a simple tight for loop. So it sort of makes sense that the iterative solution would be faster than the recursive. And were this again a production concern, write up a little bit of an explanation, send out the analysis, and then we would just choose as our implementation of factorial iterative, possibly again with some more exhaustive testing on possibly a variety of machines if that was necessary. But now let's go see what other information we've gathered. We have some hidden information, and hidden dimensions are anything that we can at any point choose to hide some particular column if we desire, but the ones that are hidden by default are things that are different for a variety of runs, but probably aren't that useful in your decision-making process, like the trial ID. The trial ID isn't particularly interesting when doing data analysis, and which instrument you use. I mean, we obviously know that bytes was probably calculated with the allocation instrument. Runtime was obviously probably calculated with the runtime instrument, so we don't concern that. And then a variety of instrument options. In the invariants, we have 705 of them. This is where things get very interesting. We record the host OS version was 10.8.4 for OS 10, and we record every single flag that the JVM knows about. There is no possibility of having one of these flags altered and publishing this report that says this is the great performance I'm seeing, and then find out later that, oh, it was because somebody had set some esoteric JVM flag that drastically altered the performance. That's always recorded, so you can always go back and find all of that information in this very, very, very long table. But because most of the time it's not particularly important to you, we hide them away in this invariance. So that is our first introduction caliper benchmark. I hope that the whole process was useful to observe. Again, let me real quick run through that. We've got benchmark methods. We label them with benchmark. We have parameters for things we might want to specify to vary our benchmarks. And then we can use the Maven exec plugin to execute our benchmarks relatively easily. No custom main methods or anything like that. And at the end of every caliper benchmark, we get a lovely results table in this web app with an opaque, unguessable URL just for you. But I do highly recommend logging in and specifying an API key so that you can have a collection of your runs that you can reference later, and you don't have to constantly keep track of these URLs. Again, hope this helped, and thank you very much.